In this section, we're going to discuss the chain rule for finding derivatives. And it's going to expand the types of derivatives we can find greatly. Let's kind of remember where we have come from. When we first talked about finding derivatives, we used the limit method, and that was really the definition. Okay, that's really where the derivative came from. That was by definition. Now, I didn't mention it at the time, but these rules that we start seeing here, for instance, after we did the limit method, then we found out there's some easier ways to find the limits, and that is we use basic rules. And most of these basic rules came from people like Isaac Newton. They're the ones that helped us be able to find these derivatives without going through that long process of calculating a limit. Then after that, we expanded the rules we could use by using a product rule and a quotient rule. And that allowed us to find derivatives of more complicated functions or situations. And today we're going to discuss the use of the chain rule. And that's going to open wide all the types of things we can find the derivative of. So let's begin. I'll make a statement of the chain rule. Okay, the chain rule says this, that if we have a function, f of x, that is actually a composition of functions, for instance, it's v of u of x, so we actually have two functions involved here, then the derivative, f prime of x, would be equal to the derivative of the outside function evaluated at the inside function. So v prime of u of x, and then we multiply with the derivative of the inside function. That's what the chain rule says. Now, quite frankly, for us, that's almost unintelligible. We don't have a clue of what that means. Let me show you an example of how we could use this, and then we'll kind of streamline the idea. Suppose, okay, this is not really what we're going to be doing overall, but it's to show you what this chain rule is about. Suppose that we have a function v of x that's equal to x to the fourth power, for instance. And suppose we have a function u of x, which is equal to, let's say, x squared plus 1. Okay? Now, from those two functions, let's create a new function, f of x, that is v of u of x. Now, if we remember the way compositions work, then that would tell us, let's see, u of x is x squared plus 4, so this becomes v of x squared plus 1. So now x squared plus 1 becomes the input into the function v. And so that means every place we see an x in the function v, we replace it with x squared plus 1. So f of x is actually x squared plus 1 to the power 4. Now the chain rule tells us how to find the derivative. And to find the derivative, we need several pieces here. We need to know the derivative of v, and we need to know the derivative of u. Well, if we look above, v prime of x is certainly just 4 times x cubed. And u prime of x, of course, is just x squared plus 1 is u, so the derivative of u is what? Just 2x. Now, we also notice in the chain rule that we've got to calculate this amount. That is v prime evaluated at u of x. So v prime of u of x, well, u of x, of course, is x squared plus 1. So what we end up doing is we put an x squared plus 1 into the function v prime. So that means where we see x's in v prime, we replace them with x squared plus 1. And so that would mean that we have 4. This is in our v prime function. And then instead of x cubed, we have x squared plus 1 cubed. And now we're ready to build the derivative of f. The derivative of f says it's v prime of u of x times u prime of x. And we've already got these components. V prime of u of x is 4 times x squared plus 1 cubed, and u prime of x is just 2x. And then, of course, we could simplify that and write it as 8x, the 4 times 2x, times x squared plus 1 cubed. Now, in this setting, it's hard for me to point. Well, actually, I can't point. I have to kind of draw arrows to kind of remind you of what we've done. But what I want you to do right now is I want you to concentrate on this part of the derivative. Okay? Concentrate on this part of the derivative and go look at the original function f. And that's right here, isn't it? There's the original function f. And notice, this kind of looks like the power rule here. Because what we did is we took that exponent of 4, see the exponent of 4 that's on this function f, and we wrote it in front of the expression. There's that 4, that exponent. And then the new exponent we've got here, 3, is 1 less than the old exponent. So that's kind of like the power rule we had before. Now, the part that we have out here, though, this part, notice that this part is the derivative of the inside of the original function. See, the inside of this original function, inside those parentheses, is an x squared plus 1. And what we have here is the derivative of that x squared plus 1. And so, really, we're going to see that the chain rule can be used in a lot of situations. But the way we're going to use it right now, we're going to replace it with something that's called the general power rule, which is a result of the broader chain rule. So I'm going to make a statement of that on the next page. Now, I want to make, again, a point. We saw the chain rule on the previous page, which is very convoluted. There's a lot of extra pieces in there. And we're going to boil that down to something that we will really use every day. Instead of trying to remember the chain rule, a result of that chain rule, a result of the broader idea of the chain rule is something that I'm calling is the general power rule. The general power rule. So this is kind of an expansion of that basic power rule, that basic rule we call the power rule when we're talking about the basic rules for finding derivatives. So let me make a statement of the general power rule. This is something that you're going to want to practice, and it takes practice. It's not so much that I worry about you remembering this name, except that I'll refer to it in the future. Here's the way the general power rule goes. That if f of x is a function that is of this fashion, that is, we have a u of x raised to a power. In other words, we have something in parentheses that has a power on it. And the thing that's in parentheses has x's in it. That's really what this is saying. Then the way we find the derivative of f, that is f prime of x, is this. We bring the exponent down, the exponent of n, and we write it in front of the parentheses. And then the new exponent we have, of course, is 1 less than the old exponent. So that looks very much like the regular power rule. Except inside the parentheses, we don't have just an x. That is, this u of x is complicated, maybe. What we do next is we multiply that. This is the part that we have to remember. This is extra. We have to multiply what we have here with the derivative of what's inside the parentheses. That is what the exponent was on originally. So kind of let me write this a little differently, kind of almost in layman's terms here. Suppose f of x is equal to some expression. So here's the idea. We have parentheses, and inside the parentheses we have an expression. It's not just an x. And on those parentheses we have an exponent. So that the expression is the u of x above. Then, okay, the way we find the derivative of f is when you put the exponent, the old exponent, in front of the parentheses. We decrease the power, decrease the exponent that's on the parentheses by 1, and then we multiply with all of that the derivative of the expression that's inside the parentheses. And that's kind of layman's terms, not quite, of course, but that's the idea. So this we're going to put to use a lot. Let's look at the first example, and then we'll do many examples to get used to how we manage this. Now, I guess I want to do this problem two ways. Let's say we're given a function f of x is equal to, let's say, 2x minus 3 in parentheses squared. And we're supposed to find f prime of x. Okay? Now, if I didn't know about the chain rule, so this is one way to do it. If I didn't know about the chain rule, then probably what I would do is I would write f of x out. That is, 2x minus 3 squared, of course, means 2x minus 3 times 2x minus 3. So I would expand this using FOIL. And after I expanded it, I would end up with 4x squared, when you could do that on the side, minus a 12x and plus a 9. So that's what I would end up with when I expanded it. Now, when I take that information and I find the derivative, we can see very clearly here that the derivative, just as finding a derivative of a polynomial, f prime of x would be 8x minus 12, wouldn't it? 2 times 4 is the 8, x to the first power, because we reduce the power by 1. And a constant times x derivative is just the constant. So we get 8x minus 12. Now, let's use the general power rule. Okay, so this time we're going to use the general power rule instead of expanding. Okay, here's let me just rewrite the function so we have it in front of us. Now the general power rule is actually about finding derivatives of polynomials that have exponents on it. That is, expressions of x inside parentheses and an exponent on the parentheses. So the derivative, using the general power rule, says bring down the old exponent. So the old exponent is 2. We put it in front of the parentheses. And then reduce the exponent by 1. So when we reduce the exponent 2 by 1, we just get an exponent of 1, don't we? And then multiply with the derivative of what's inside the parentheses. What's inside the parentheses is 2x minus 3. So we'll come and we'll actually calculate that here in just a moment. And of course this 1 was the old exponent, subtract 1. Now, as we kind of clean up and do a little work, an exponent of 1 we normally don't write, do we? So we'll just say this is 2 times 2x minus 3 that are in parentheses. And then when we calculate the derivative of 2x minus 3, don't you agree that we just get a 2? Derivative of 2x is 2, minus the derivative of 3, being a constant, just gives us 0. So now what you see is that f prime of x, we have a 2 in the front, we have a 2 in the back, so it's actually 4 times 2x minus 3. And then, of course, if we expand that, that is, we multiply that 4 out, we get 8x minus 12, which, of course, is the same result we got up here, just using basic rules and a little bit of algebra to get started. Now, the above, part A, worked just fine because the exponent was 2. But what if the exponent would have been 7 or 8? We're not going to write out 2x minus 3 times 2x minus 3 times 2x minus 3 times 2x minus 3 over and over. That would be very difficult for us to even multiply it out. But this general power rule would still allow us to do that. So this is the introduction to the general power rule. I'm going to stop this video, and we'll create I'll create a couple of other videos that have more examples in them.